Okay, hello everybody. All right, hi MATH7502. Can you hear me? Thanks. See a lot of yeses, great. We'll start in a minute. We'll do our 3-hour session. And I'm still setting up just a bit more. Okay, 30 of us here. All right, 5 in the afternoon in Brisbane, Australia. Hi to everybody. We are in week 3. A lot to do today. We'll take it at a solid pace. I'm sure maybe there are a few questions just before I start. So are there any questions? No, nobody wants to come out with a question. I mean, you could interrupt with questions at any moment. It's not interrupt. You can just ask questions. So next week you have quiz 1. There were a few questions in Piazza about quiz 1. just key reminders, the quiz is closed material. So that means you cannot and will not use any other material except for an A4 page. That's one A4 page, one page like this, two sides, A4 page. On that page, you'll prepare your formulas, everything you know. That preparation is kind of a learning process in its own right. So the quiz will be available in 168 hours minus 5 minutes. There's 168 hours in a week, I believe. And then you do the quiz. Now, you don't need to have a printer in your house. You can just write your answers on a piece of paper, take some photos, format a nice PDF file that has the photos according to all of the rules that are here. So maybe practice that just before if you haven't done one of these at UQ. So you submit a single PDF and it can't be too big, none of these 80 megabyte things. If you have issues with that, you go to a PDF compress utility, you submit that, you submit it to this very short address. It says Math Data Science Bridging Submissions. So you submit it there, and you also submit a voice recording like those beautiful voice recordings that you've had. Okay, and we'll actually look at a practice quiz today, or it's not a practice quiz, but it's something that can give you an indication what the quiz would look like. Okay, and I've got some questions. How many questions are there in quiz one? I'm not sure. So a few, but you'll see a practice quiz today. I'll show it to you. You know what? Let me just show it to you right now. Here's a practice quiz. It's also in the GitHub repo. It's called a demo quiz. You also have a PDF of it in the GitHub repo. This is what a demo quiz looks like, an example of what quiz one can look like, but it won't look like that, okay? So it has 2 questions with 5 items per question, that's 10 items. So say each one's worth 10% or something like that, okay? And we'll go over these after we actually study what this means, but that won't take so long. Okay, so that's like an example. Now the quiz covers quite a lot of things, not so much, but a lot, all this stuff. Okay, the operations here is misspelled, sorry. So it covers these things, not everything will be in the quiz, okay? Oh, that's a great question. Can you use a dictionary to look up new words? Yes, yes, yes. I'll try to even make that explicit on the website, okay? So, more questions on the quiz. Okay, now I get a question about Julia. So first of all, just the quiz does not involve you using Julia. In fact, you're not allowed to use Julia in the quiz, and you should state that you haven't used that in, or you just use the A4 page and a dictionary and a calculator. And if you're not allowed to communicate with anybody. But if you don't have a scientific calculator, you can use a calculator on your phone, but it's a scientific calculator on your phone. So addition, subtraction, experimentation, etc. Different question. I get 3 kernels, Julia 1.42, Julia 1.5, Julia Pro, Julia and Jupyter notebooks. Which one do you recommend? They're pretty much all the same. It doesn't matter. But the same kernel that you use, make sure you use the same kernel because you're installing packages. So those packages are installed for that specific kernel. In fact, packages can be also installed for a specific environment, something called an environment, but we didn't speak about Julia environments. Are there more questions, thoughts, anything of that sort? Okay, let's get to it. So we're back, and we'll get to this demo quiz thing. So I'll go back to this core linear algebra with Julia to unit 2. And we're now at the heart of what's called boring linear algebra. Now, it's not really boring, but linear algebra that deals with equations, okay? Equations. So we're going to pretty much close that today and also move on. But we'll also see something quite cool, which is called LU factorization. And then number 6 here is completely not related. And I also hope that today we'll also be able to start unit 3. Which deals with linear transformations and vector spaces. We won't speak about vector spaces, but we'll speak about linear transformations. Okay. So that's a plan for today. Okay. And of course, some of you have probably started your assignments, so the practical this week will deal with the assignment. So the tutors, Sam and Walla, don't have any specific material prepared for the practical except for some knowledge of the assignment, and you can use their help to kind of get ideas and tips for the assignment, and they might help with questions that are related. There's also a question here on the chat. Can I write a PDF on iPad instead of paper? Sure, no problem at all. So you can also type it, but typing is a bit time constrained. I wouldn't do that. I mean, your time is a bit short, okay, so I wouldn't type it, but you can certainly write an iPad. All we need is a legible quiz submission, okay? And you get a bit of time for submitting that as well. Okay, so towards the end of last week, we were dealing with linear equations. This is kind of a basic system of linear equations that you can represent here as a matrix form, AX equals B. And you've all done this in one way or another elsewhere. I mean, this is in a sense prereq. Well, it's part of the prereq that you need to do. You kind of need to know what that is. And, you know, we solve this linear equations by actually subtracting one equation from the other. And the process that does that again and again is called Gaussian elimination. And we'll revisit that in a bit more depth today. Okay, so this is pretty much what we did. And then I also showed you the backslash operator, which is kind of the built-in solver for systems of linear equations, and it even does more. Okay, so I'm skipping all of that. And we've also seen that at least algebraically, you know, you can solve the system of linear equations by multiplying the left-hand side and the right-hand side of the matrix by the inverse of A. I mean, the assumption here is that A is non-singular, i.e. A is invertible, i.e. its determinant is not zero, and then i.e. its inverse exists and is unique if the inverse is unique. Okay. All right. This was a system of equations that is singular because even though it looks like two equations and two unknowns, the second equation is just a multiple of the first. Okay. Sorry, it's not that the second equation is a multiple of the first, but the second left-hand side is a multiple of the first left-hand side. Okay, so this matrix was singular. And sometimes you have more equations and unknowns. Now we'll deal much more with the situation of more equations and unknowns, less equations and unknowns, etc. when we speak about vector spaces next week and onwards. But today, with respect to linear equations, our story is about solving the system of equations, doing it systematically, and also being introduced to our first matrix factorization, okay? And that matrix factorization is PA equals LU, or sometimes just A equals LU. It's called the LU factorization. Now, I'll explain what that is, and we'll spend quite a bit of time on that, okay? Now, just so you know, in this course, we're actually going to have all kinds of factorizations. So there will be the matrix A is U transposed sigma V, which is called the singular value decomposition. That's a decomposition is synonymous with factorization, or there will be the factorization A equals QR. Okay? Or today, A equals LU. Now, all these factorizations are a way to represent some given matrix, which is really the basic main object of this course, is a product of two or maybe three other matrices, okay? And such when these matrices have specific meaning. Now, in the LU factorization, we call it the LU factorization, but we also call those matrices L and U. They stand for lower triangular and upper triangular. We'll see what they are, okay? Similarly, the QR factorization, we call the matrices Q and R. We'll probably get to QR factorization, which arises from the Gram-Schmidt procedure in about a week and a half. Yeah, okay. And this singular value decomposition way towards the end of the course. All right. So, and here P is a permutation matrix. We'll get to that as well. Okay. But let me now slow it down, and we'll deal with a system of equations that has a left-hand side matrix, which is this matrix A. Okay. Now I'm not even writing the system of equations, but I'm saying here you can think of AX equals B. Okay. You can think of AX. But we're just going to focus on the matrix A at this point. All right. So let's think about this matrix A. And as we do that, we'll think about doing Gaussian elimination steps, which try to solve the system of equations in the same way that we did for the last one last week, only that one was 2 by 2, but this is just going to be a bit more general. Now, just a comment about this. Let me digress and go to assignment 1. So here's assignment 1. So there were a few questions. Hey, is this a typo? Why do we have, like, you need to look at this system of equations. Why do we have here, for example, 4x and 3x? Is this a typo? Is this supposed to be a z? No, I mean, it could have been a typo, but in this case, it's not. The idea is that the system of equations is not always presented to us in the nice form of ax equals b, right? So if you're solving this using Gaussian elimination, you first represented it as ax equals b. In this case, x is w, okay? And x is a scalar in that specific case. That happens a lot, all right? So you need x is either as a scalar or is the whole vector, okay? So the x is a double. I assume that's clear, all right? So we're already in the world where our world is AW or AX equals B, okay? That's just a comment. And now let's look at this matrix A, which, here it is, okay? Here's our matrix A. Now, what we do, and I'm running this, okay? And what we do when we do Gaussian elimination for this matrix is we basically take the top left number and we call that a pivot if it's not 0. If it's not 0. If it happens to be 0, if this top left entry, this A11 entry happens to be 0, then we actually need to do row exchanges. And we won't deal so much with that, but that has to deal with this matrix P, okay? Then we have to do a permutation, okay? But let's assume that that's not the case, as it isn't in this case. And by the way, numerically, sometimes linear algebra software anyway does permutations for numerical stability. That's kind of a more advanced story, all right? And our goal is now to get a 0 here, and a 0 here, and a 0 here. That would be, you can call that the first 3 steps, but we'll just call that the first step. So zeroing out column 1, okay? Now, what we're gonna do is we're gonna take this row, and we'll multiply it by a multiple, such that when we subtract this highlighted row from the second row, we're gonna get a 0 here, okay? So what is that multiple? So that multiple, I'm calling L, this letter here is L, and I get it in Julia by doing L, ELL tab, okay, so ELL plus tab. Okay, that's how you get an L. And it's just nicer because this L, when I'm hitting L on my keyboard, looks maybe like a 1, and it's a bit confusing. Okay, so that's L, like ELL. That's a LaTeX L. Okay, L21. So L21 is going to be 3/10. Why is it going to be 3/10? Because if I multiply this first equation by 3/10, then I'm going to get 3 here, and I'm going to get some other things. Okay. And you see it's in the 2-1 entry. It's the second entry, second row, first column. And similarly, L31 is going to be this entry divided by A11 by 10. And L41 is going to be this entry, this 1 divided by that. Okay. Now, let's create the matrix that we'll get, and it's going to be a different matrix. It's not going to be the matrix A. Let's call this matrix A1. Okay, so I'll just evaluate these numbers. We'll call this matrix A1. And A1 is going to have 4 columns. And here I'm specifying this is a matrix after Gaussian elimination steps on first column. Okay, so this is the first row, unchanged. You see, I've got here the A1, the first row, and I'm putting a transpose. The reason I'm putting a transpose, if you do this in Julia, it just takes this as a one-dimensional array or a vector, okay? And it thinks of it more as a column vector. So it transposes it into a row. So that's the first row of this matrix. The second row is what it was minus the scalar, that multiple, L21, this scalar that I'm highlighting, times the first row, okay? And transpose all of that, okay? Oh, I guess I didn't even need to have a semicolon here. Okay. So this is actually creating like a block matrix from these four things. Okay, block matrix from 4 rows. The third row was what it was before, minus that multiple that we just found, this guy, L31, times the first row. Okay, and similarly for the fourth one. Okay, so that's going to be this matrix A1, and let's run this. And you see what we've gotten. We did not modify the first row, but we've zeroed out these 3 columns. Okay. Sorry, we've zeroed out the first column, the 3 entries under this entry, which is called the pivot, and that pivot is 10. Okay, stop me if there are questions or anything. Now, the first thing I want us to see is that this operation that we did on the matrix A1 can also be represented as and by the way, I'm teaching here, I'm assuming that most of you have done Gaussian elimination in one way or another. So I'm going directly to the slightly more advanced view, which represents Gaussian eliminations in terms of matrix operations and then LU factorization. Okay, and frankly, with the exception of that first question in homework 1, and maybe a question in the quiz, but not really, because that's too time consuming. I'm not going to put something so time consuming in the quiz. This hand Gaussian elimination is not something that you need to do, okay? But it's understanding the concept. Okay, so my next point is that this operation of subtracting, let's just do this subtraction here, okay? So taking the second row and multiplying and subtracting from it a multiple of the first row can be represented by such a matrix E21. So look at this matrix E21, okay? And this is sometimes people call this an elementary matrix, okay? So the matrix E21, what it does is when you apply E21 to the matrix A, now you need to think about way 3 of matrix multiplication that we spoke about 2 weeks ago. So when you apply to the matrix A, assume for a second, first of all, just delete this, okay? I'm just going to, just look at now E21, okay? It's written in a not so nice way. Oops. It's written kind of, the spacing is kind of not nice there, but that's okay. But look at this E21. What happened here? I don't know. So, what if E21 was as follows, is what you see now, and I would multiply E21 by the matrix A? What do I get? What's E21 times A when this is E21? What's it's just A, it's identity. Okay. Yeah, last week the answers were I all the time, now they're A all the time. So make sure your A button is firmly secured to your keyboard. No, I'm joking, I don't know. Okay, so, but that's not exactly the matrix, right? The matrix is this. So what it does is it does not touch the first row because the first row is going to be untouched. It does not touch the third row. It does not touch the fourth row. But the second row of the product, so what I want to say here is second row of the matrix product E21 times A is first row of A, that, okay, minus the second row of A. But so I should look at this. I should look at this. So what is, I should read it more like that, is negative L21 times first row of A plus 1 times second row of A, right? So that's that negative L21 and this one plus zeros. Okay, so if I look at E21, let's do E21 times A, then you see it's just one step, which is zeroing out this thing. Okay, so that first row operation is a multiplication on the left by an elementary matrix E21. E21. Right? So that's kind of nice. So these Gaussian elimination steps, that was not the step of the whole column. That was just a step for zeroing out this entry. Okay, it's multiplying on the left by E21, where E21 is kind of parameterized by this scalar L21, which is this entry divided by the pivot. Okay. We're not going to have a homework assignment to implement Gaussian elimination, but in a sense you can. It's quite implementable. At least kind of a rough implementation is not so hard to do. All right. Now let's just think, what's the inverse of E21? So E21 does a transformation on A. It converts A to something else. This thing is no longer A. Okay. This is it's also not this A1. It's like this intermediate A, which has this after one iteration. So if you'd want to kind of say, no, I changed my mind. I changed my mind. Mistake, undo. Okay. So to undo, I'd want to go from this guy back to A. Okay. So the only thing I would need to do is, instead of having this negative L21 here, I'll need to have a positive L21 here. Okay. Now, of course, you can check. You can check that the inverse of this, you can check that this is the inverse just by doing the multiplication thing, that it goes back. Okay, so you're kind of bringing it back. No, I'm bringing back I'm adding the 0.3 times the first row. I'm not subtracting. Okay, so just keep in mind that these elementary matrices are invertible with a very explicit inverse. By the way, what is side comment? What's the determinant of E21? Just to see we're kind of in shape. The determinant, it's 1. Zhang, why is it 1? Why is it 1? How do you see it's 1? Because you're probably because it's upper, and then you're multiplying the diagonals, and the diagonals are just 1, right? Okay, thanks. All right. Similar to E21, there's also E31. Same guy, only this guy does a second operation. Okay, that's E31. You see, that's a matrix E31. Let me run this. It's inverse of E21. Then there's E31. And similarly, there's E41. So these three E's, you could think of the first operation. Now think here, I'll put here like in comment, times A, okay? So you apply, what we did, I should write it like this. We applied E21 to A, then we applied so we applied E21 through A, then you apply E31 for A, then you apply E41 to A. So these three applications, their multiplication is just an application of something bigger, which happens to be, I mean, matrix multiplication of elementary matrices is nice, so you just add up those entries. So you just add them up here. And that just comes from the fact that this matrix is so sparse with so many zeros. Okay. Now, also notice, just so you see, that because these matrices, it doesn't matter, because each one you've touched here, you did the operation on the second row, on the third row, on the fourth row. You could have done the fourth row before the second row and vice versa. You can't move to another column. We're still just in the first column. But you could have operated on this row, on this row, or on this row in any order that you'd like. And this is basically embodied in the fact that, look, that these matrices commute. So look, here I have E31 times E21 times E41. I have them in a different ordering, and it's the same product. Okay. Now we're actually, I think I have this down below, but we might as well do it now. We're actually calling all these three matrices with the danger of abusing notation. So we'll call them L1, and L1 is going to be E41 times E31 times E21, what we just did. Now I have a question from Jonathan. In that case, it commute, but it's not always the case, correct? No, so it's elementary matrices always commute. Okay, so this, by the way, can be a quiz question. Say, what's an elementary matrix? An elementary matrix is basically I'm now just defining it by words. I'll never not define it by writing. It's in one of the references. Certainly in, for example, in this one. Okay, that's an elementary matrix. And this is the one of the references. Okay, but in many other places. So an elementary matrix is an identity matrix and another entry, which is minus the entry divided by the pivot of the matrix. Okay, so when you have such a matrices, they commute. Of course, when you have such matrices, they commute. Of course, if you take others, they won't commute. Okay. All right. Now the product, their operation is L1. Okay. So just to see, so look, we've done here this. We did here. This was a manual calculation. This here was a manual calculation, right? We actually did it by hand. I mean, I didn't write it by hand, but this is like writing it by hand. But so look, this is this 10 here. And now notice what happens here. The entries here change, right? In these different columns. I mean, that's kind of the point. The first row did not change, but the other rows in different columns, the entries changed. Our A, you see, for example, this is now 11.4. This is a number we didn't know about when we saw this original matrix. Okay. So how do I get this matrix A1 in terms of A and L1? Well, what I just need to do is I just need to do L1, apply to A. So this was, in a sense, that is a matrix A1. Okay, I'll write here A1 again, just so we see it. Okay, same way. In out 12 and out 13, same way. So first column operation of Gaussian elimination is multiplication by this matrix L1, which in itself is a product of 3 E's. Okay. So now we've got our A1. Which column do we work on now? We work on the second column. We work on the second column. Now, again, we might have seen then here a 0. And by the way, that 0 can appear like after the fact. It might be that the 0 is not apparent when we are working on the original matrix A, but suddenly this thing I'm highlighting is a 0. And then we might need to permute rows. Okay, because if you think about it, by permuting rows, by permute I mean change, yeah, permutation, make a permutation of the rows, switch rows. So permuting rows, you're not changing your equations, right? If I was also permuting the right-hand side, the vector B. But we're not speaking about the situation just yet. Okay, so what we're doing now is we're going to the entry L32, which is this 3.6 divided by the pivot 11.4. Okay. And L42 is going to be this 3.8 divided by the pivot 11.4. And this is how we make the matrix A2. Matrix A2. So the matrix A2 had the first row for matrix A1, which is also first row of A. Okay, and it has a second row from the matrix A1, which is not the first row of A. And then it does those two operations here, just like we've done before. Now, of course, let's just represent this in terms of the matrix L2, okay? So to get to A2, we'll represent the matrix A2. So now, if we were in class, we'd have like chanting, what is this L2? So what I'm gonna do is I'm gonna, just like in a very barbaric manner, I'm just gonna write the identity first. Of course, if you're doing this programmatically, you know, and is this identity? No, it's a non-identity. Okay, you can maybe program this in a better way, but this is still just a 4x4 example, even though we're using Julia as an 8. Okay, I'll answer that question in a second. And now we want to change some entries here. So think of what I'm going to put here. And John is asking a nice question. Do elementary matrices of different columns commute? I think the answer is no, but I didn't check it. So you can check it. So John's asking a nice question. Wei Jian, thank you. So do elementary matrices of different columns commute? Okay. So does E31 and E32 commute? You can check it. If you see that they commute, it's not a proof that they always commute, but if you see it don't, you immediately get a counterexample, so it's a proof they don't commute. Okay. All right. So I don't know, basically. but that's a nice question. Okay, so here is L2, L32, like Zhang said, minus 3 minus, right? And minus L3, 4. Okay, that's our matrix L2. L42, sorry. Okay, so column 2. Exactly like Ben said. And then we can also, again, apply the matrix L2. What am I going to multiply L2 by? What is it going to be applied to? What to get that second column by A? Well, A2 still doesn't exist. We're now defining L2, A1, right? So somebody said A2, no. A2 is going to be L2 times A1, or instead of A1, let me write times L1 times A. Okay, this thing I'm highlighting is A1. That's A1. Okay, so that's our A2. See, this is A2 that we created, same guy. The end is near. The end is near. We still have one more column to work on, this third column, okay? And we want to get rid of this guy. And this guy is going to be 2 minus 3, 3, 3, 3. You can 3, 3, 3, 3, 3, 3, 3, okay? You know, so 200 years ago, there were people in France that wanted to improve our world and make us use a base 12 number system. So we use a base 10 system because, you know, 10 fingers, I've got like 9.5, one is cut, okay? But we've got base 10 system, okay? I should use a base 9.5 system. But they want to use a base 12 system. And the reason they want to use a base 12 system is then representation of thirds would be easy and we won't have this stupid thing that we have to do 3 like that, okay? But we're with base 10. So whenever you get to something that's a multiple of 3, it doesn't work. Because the number 12 is nicer than number 10. It's divisible by 6 and by 4 and by 3 and by 2. Okay, anyway, enough telling you things that are completely not relevant to what you need to know. So L43 is this, and here we do our last column Gaussian elimination step, right? Look, so we took this from A2. I could have written here instead of A2, I could have written A1 or A. I could have written here A1, and this is A2, right? So we keep the columns from the previous, we keep the rows from previous guy, we do the last step, say 3. And, oh, by the way, here I'm repeating myself. I'll just delete this, delete this, delete this, delete this, delete, delete. And finally, the matrix L3, using the same reasoning, is just the matrix E43. Okay, that's which we never wrote the other elementary matrix. Is that? So if I do now L3 times L2 times L1 times A, okay, so this here, in this first brackets, I'm just putting the brackets so it's kind of clear. So this was the first step of Gaussian elimination. Again, first step is first sequences, first column. This is second step, second column. Now the third step, or step we can call super step, and we get this. Oh, did we get an upper triangular matrix? Was our matrix upper triangular? Is this an upper triangular matrix? We wanted a 0 here. Yeah, not quite 0. Again, the French could have saved us from this. Now I'll get back to the French. The French could save us. So if we would have done like, of course, there are better ways to do this. Okay. Okay. Then you'd go here and it'd be a bit better, or not. Okay. Yeah, okay. But there's numerical error. It doesn't have, it's actually not stemming from this guy. Okay, there might be some other roundup error and stuff like that. Okay. So for all we care, this thing, it looks a bit scary, but that's a 0. And now we've got an upper triangular matrix. Okay. So let's go back now to the system of equations. So I'll share the visual, the scratchpad real quick. That should work, I hope. Yes, so what we've had, we started with A x equals B. We're not worrying about this red bit for now. We're just thinking about the matrix A. And we did this thing that sometimes you can write, we'd go from A, we went from A, and let me just to represent A, and you know, A is like this, I'll write like dot, 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 dot. These X's mean some entries, okay? And one more, okay? So this is this matrix A, and then we went from and let me put this like this, A like that, so you'll see why in a sec, okay? So we went from the matrix A, you can put a column, we went to something which is the same guy, and then 0, 0, 0. And here I'm going to put like x tilde, x tilde, x tilde, no, x tilde, x tilde, x tilde, x tilde, x tilde, x tilde. Okay, this guy was L1 times A. Okay, that's what zeroed out these guys. And these x tildes, you see, they're different. I mean, these x's here are the same as this x, but those x tildes are potentially different because we did row operations. And then we went to a different guy, which is x, 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 0, x tilde, x tilde, x tilde, 0, 0, x tilde, tilde, x tilde, tilde, 0, 0, x tilde, tilde, x tilde, tilde. And this was L2 times L1 times A. Okay, well, I shouldn't put this times now, not to confuse, just that's a product of these three matrices. And then, I'm sorry, it's a bit long, but just so you see, okay? And then we went to x, 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 0, x tilde, x tilde, x tilde, 0, x tilde, no, 0, correct me if I make mistakes, please, x tilde, tilde, x tilde, tilde, 0, 0, 0, x, how many tildes on this x? 3. Tilde, 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 it's kind of fun. Okay, so that's L3 times L2 times L1A. What matrix did we get? What's its adjective? Please don't say red. What's its adjective? Elementary? No, we didn't get an elementary. It's an upper triangular matrix. Upper triangular matrix. Upper triangular matrix. Exactly. What name should we give it? Choose a good letter. Good letter? U. Good letter. Okay, so let's call this guy U. Okay, so basically what we've seen is that L3 times L2 times L1 times A equals U. Now, we like the upper triangular matrix because if we take an upper triangular matrix U, for example, okay, just if we were presented with a different problem and you had an upper triangular matrix U and you multiplied by some vector W, and you had some right-hand side, let's call that right-hand side C, okay, then this is easy. I mean, it's so easy, we're actually going to code it from scratch together today. Okay, so we like upper triangular matrices. Okay, but we're still not exactly there. So what I want to do now is I want to go and I want to do A equals something times U. So how can that U is the same U? Okay, this U is a U. So how would what's going to be that something? What am I going to put here? L. Of course, that's it. Inverses of L. Exactly. That's exactly what you guys are saying. Exactly. So what we're going to put here is the inverses of L. Okay. And so that L is going to be L3 inverse, L2 inverse, L1 inverse. Okay. So I multiply by the left. Now I'm going to scratch a whole lot on this. By L3 inverse, L3 inverse. By L2 inverse, L2 inverse. By L1 inverse, L1 inverse. And that's how we get our matrix L. Okay. Now, the nice thing about L, let's put L back to be green. The only color coding I have here is a bit of random color coding. So that L is actually going to turn out to be lower triangular. Okay. And the entries which we have here are going to be the scalars L21, L31, L41, L32, L42, L43. Okay, so that's actually the matrix L. Okay, this is how you get the matrix L. All right. Then, and we can do that. We'll see that in a second in Julia. So if this is a matrix L, so look, L is lower triangular, U is upper triangular. Okay, L is, sometimes people, I think they call this, people, I don't know, speaking like people, I don't know. Sometimes it's called unit lower triangular because this is actually has units. Whereas U is U unit lower, is a matrix U unit upper triangular? Is U unit upper triangular? No, not necessarily, but typically not, right? I mean, unless we're super, super lucky. So these X's here are not going to be units. Okay, we'll speak about that. Okay, and the question by Rob, are they opposite sign? The scalars, yes, they are. Okay, and they actually encode something. So if you were now, so say now that you know this and you've internalized already, and you meet somebody who knows Gaussian elimination, and you want to explain to them, what does a matrix L encode? What does a matrix L remember? What does it remember? What does a matrix L remember? It's basically like a time machine, a history of the Gaussian elimination steps that you did. That's what it is. It's a recording of the Gaussian, it's a recording of what the algorithm did. Like this was like this L21 is a recording of that operation you did. And that's a recording of the operation you did. And that's a recording of operation. Then you went to this recording and this recording and this recording. They turn into perfect circles as well. Okay, so that's a matrix cell. Okay, let's go back to Julia, to Jupiter. How do I do this? Just like this, share screen on the computer. All right. Now, let's use the Julia command LU. Okay. Now, by the way, let's try it before. Let's do like this. This will crash. LU of A. Why is it not defined? This is kind of a Julia question. An annoying, basic Julia question. What package will have LU? Okay. I mean, it's, you guys don't want to waste your energy on non-important things. Linear algebra. Right. Thank you. Okay, so when I did LU of A, what I got here is first of all, just some Julia stuff. What I get back is like a struct, okay? It's a struct, so I can call F is like it's like a type, okay? So if I do type of F, it's not completely not related to linear algebra, but related to Julia, it's an LU object, okay? Now an LU object has all kinds of things. Specifically, it has a factorization and remembers two main important things. It remembers L and it remembers U, okay? It actually remembers more, it remembers permutations, but we'll only speak about that later. And I actually set this specific matrix so that no permutation is needed, okay? You can do question mark LU and see the help for LU, okay, after a while. All right, so now you can also do, yeah, so it tells you a whole bunch of things. Now you can also do, we could have also done this, we could have also done L comma U equals LU of the matrix A, and that actually, it returns the LU, but there's also, L is already a matrix. So let's look at the matrix L. Here's a matrix L, okay. So this matrix L is, let's just actually construct it manually because that's what we did. All it has was L21, L 2, 2, no, 1, 0, 0, L 3, 1, L 3, 2, 1, 0, L 4, 1, L 4, 2, L, come on, 4, 3, 1. Okay. Same guy. So this is our manual construction of L. L manually done. Okay. So L gave you this. Now, if you look at the matrix U is this guy, which is our upper triangular matrix. And if we look at the one we got, which we called A3, that was our U, same guy. Well, LU, Julia's LU managed to, this 10 to the minus 7 entry was actually a 0, and Julia's one is smarter, better. Okay, did things better than what we did. Okay. So at this point, what is going to be L times U? A. Very good. Is A. Okay. That's A. Is it A? I'll just put what A is again. It's A. This 0 is this 10 to the minus 16. We live in a numerical world. Congratulations, you have factorized the matrix A. Okay, you factorize the matrix A. All right. Now the title of this section was, and I won't dive into this too deeply. I mean, last year I didn't even teach LU, unfortunately. I see why I should have. Okay. So PA equals LU. So what do you think this P stands for? If you looked ahead, or if you've done it, or if you haven't, or maybe I said it a bit, permutation. Okay. So the LU decomposition works if we don't do row exchanges. But if we do row exchanges, then something more intricate is happening. It's not just that we're multiplying A from elementary matrices. We're actually doing A times elementary. So this is your left, so I should do like this, your left, yeah. Like A times, you look at your left. This is A times elementary matrix times permutation times elementary matrix times permutation, elementary matrix permutation, elementary permutation. So we're actually doing all these permutations. Now, you really, really mathematically need to do the permutations. You need to permute rows if you have zeros here. Okay, like for example, maybe you had a 0 from the go, or maybe a 0 resulted. But actually, numerical software also permutes rows just to get better numerical stability, and we're not going to speak about that. So there's a course going on this semester. Maybe a year from now you'll take it, numerical linear algebra. Now, there's a question, do L and U represent the upper and lower triangular versions of A respectively? You can't really call it the version of A because L by itself does not represent A and U by itself does not represent A. But L and U together are a lower and upper representation of A if this P is identity. And back to what I was saying, if you need to do permutations, P is now going to be the identity. Okay. So just after the break, we'll see this. We'll actually see how this works a bit, but we won't deal with it too much. And we want to get into uses of LU. So yeah, so LU factorization represents the steps of Gaussian elimination, because at the end of the process, what you have is, of course, we did here, the process is one command in Julia, but at the end of the process, you have this U factor, which is an upper triangular matrix, and the L factor represented the steps of Gaussian elimination. And I'll show you after the break how we can use these matrices. Okay. 5:50. Any last question before the break? Okay. So see you at exactly 6. That's Brisbane time. What is it in mainland China? Is it 3 now? Is it 10 to 3? What is it in China? 10 to 3? 10 to 4. 10 to 4. And in Philippines, I think it's probably 10 to 5, maybe. I'm guessing. I'm not sure. Okay. Anyway, see you in 9 minutes. 4 as well. Thank you. 4 as well. Okay. Okay, I'm back. We'll start the class just in 5 minutes. Are there any questions? No, so feel ask anything. Okay, so Jonathan's asking an important question, an administrative question. So trying to keep the local files updated with checkpoints on Git. Work away a way to do this. So I'm surprised that you're trying to pull. I mean, just doing a Git pull. So I'm actually not sure, right? So it's like you want to fork again and again. Does anybody have an answer? So some people here are software devs, where others have not used Git at all. So I don't have an answer, but that's an interesting question. So you go to the GitHub repo, and it's fair enough. I mean, we keep changing it, we keep pushing. What is the best way to kind of automatically pull? So I guess you can download the zip, or you can pull. You can clone the repo and pull an update. I'm actually not sure. Sorry, no quick answer. So because I haven't done this, I haven't kind of tracked somebody else's repo, and but git pull should work. No? Okay, so otherwise just pull again every. No, yeah, I mean a manual pull, a weekly manual pull is yeah. I mean, for me, if I go to this, okay. Oh, so for example, here I've updated this, right? So this is, by the way, what I do. So this is my Unix terminal or Mac OS, whatever in this case. And I'm a bit sloppy with this whole thing, so I would add dot. It would add the file, git status. You see, it's now in the what's called the staging area, and then I would do a git commit. And during class, that's a message, and I've committed it to the browser, and then I push. Now, I guess if somebody else was working on this on the remote on GitHub, I would need to do a git pull every time, but I'm up to date because nobody made a change. Okay, let me actually make a change. Let me go to this README file here, and say 2020 space. Okay, I'm going to add a space. Commit the changes, won't even put a comment, okay? So now I'll go here, let's do git pull, and you see it pulled readme.md, the two changes. Now because I've got this as my, but I'm not sure about the language, I'm not a GitHub expert, but right. So if you were like me, connected to this GitHub repo, you've configured it as a remote, you can pull just like that. And you can do that on GitHub desktop. Now, many of you don't use GitHub yet, and that's fine. And if you're worried about so many other things, that's not what you need to worry about at this point. You can just, of course, just go here and pull the files. Sorry, that's all I can say on that. More questions? Is anybody here? Everybody's either in Australia, China, or the Philippines, I believe. Or did I miss somebody? Do we have a student from Uzbekistan? I don't think so. All right. Let's get back to business. We got a lot to do. So we're here. All right. So we've got our LU. Great. We've got our LU, right? We've got our L and we've got our U, and L times U is just our matrix A, etc. here, let me just delete a few rows here, a few entries, okay? And, you know, L is the inverse of L3 times L2 times L1, okay? Now, you cannot, let me also say now that you can get LU, here, LU, the third thing it returns. I mean, LU, the struct has several things, but the struct that this returns. But the third thing is this P. So let me run this command. So what you see in this P, you see L is just the L, display U is just a matrix U, and P is this permutation index. Okay, I could have also done. Let me just do it like this. And one more time, I'll just do this. I'll do one row below. I'll do LUA. Let's call this F, the factorization. I mean, we're factorizing here many times the same thing. And I'll do F dot capital P. So capital P, what do we have here? The identity matrix. Okay. The identity matrix matches this permutation. This permutation is the trivial permutation. It means don't permute things. Don't permute things. Okay. And indeed, with this situation where no permutations were needed, if I do A minus L times U, we're going to get zeros, right? It's all zeros, okay? Zeros. However, let me now take the matrix A and just modify it a bit by switching a row. Okay. So let's take A and let's switch a row. And let's hope that LU decides to use a different permutation. So going here, let's call this AS, like A switched, okay? A switched, okay? So I can do this manually. I can do this. Let's do it like that. Or of course I could have done it in a much smarter way. But what I've done is a switched, switched, second and first row. This A, if I now do, whoops, sorry. If I now do LU of this A, this switch didn't cause any trouble. So let's do LUA dot permutation. Oh no, okay. Okay, good. So this switch, if I now do call this LS, US, PS, these are the results of this LU decomposition. If I now do LS times US, let's see if that equals the matrix A. So the matrix AS, I'll subtract the matrix AS. And no, it isn't. Okay. Bad. Okay. So A is not equal. A does not equal, A does not equal L times U in this case. However, if I do AS with this P, okay, so look at P. P is the index of permutation. Oh, what did I do with P? Oh, PS. PS. This is not critical what I'm doing now, by the way. So it might look a bit confusing, but it's not the core, it's not the central thing. So you see this permutation switch the second row and the first row. So how do we do this on AS? I'll do AS PS, comma, colon, that takes this array 2, 1, 3, 4 and switches it back. Okay, it's actually going to switch it back to what A was originally. And I'll do that, and I'll do L times U minus that. We're going to get a 0. Okay, so this thing here is the permuted A, the permuted A. Okay, AS was like our one that actually needed permutations. Now, algebraically, a permutation matrix is like, let's look at this matrix. Let's call this matrix PP. So I'll put PP. It's a matrix. I'll make a permutation matrix for this thing. Okay, you'll see what I mean. It has 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Look, these lower two rows of it look just like the identity matrix, but the upper two rows say to make a permutation to switch the first two rows. Okay, so it's basically a permutation matrix matching this permutation. So here, the way to think about it is, again, if I multiply now this permutation matrix, look, this permutation matrix times the matrix A is going to give me the matrix AS, which is the switch one. And of course, what is, by the way, what if I multiply again by this permutation? This permutation only had a switch of two rows, right? So if I multiply by it again, it's its inverse. So the inverse of a permutation matrix that just inverts two rows is itself. Okay. So for example, what I want to say is that PP times PP in this specific case is identity. Okay. So to get now to the heading of this section, which wasn't A equals AU, A equals LU, it was PA equals LU. There's actually, it's sometimes not going to be exactly A, it's going to be a permuted A. Okay, so that matrix P is a permutation matrix matching the specific permutation we had there. And the LU decomposition algorithm will actually find you these permutations. So it won't know ahead of time what's going to be the permutation, but as it works, it might say, oh, I want to do these and these and these switches. Now, again, sometimes you have to do it mathematically because you are going to divide by 0. But other times, even if you're not going to divide by 0, it'll still do it for numerical reasons that we're not getting into. So just to finish this here, let's do now the factorization. I'll do it again from scratch, just here. We've got our matrix AS, so I'll do LU decomposition of AS. Okay, let's call this now the factorization. Okay, and then I will do F dot L times F dot U minus F dot capital P. Okay, so capital P is a permutation matrix times A times AS. Okay, this is a permutation of AS. And this is going to be A0. This is also, okay? So that's AP equals, sorry, PA equals OU. Right? You don't worry too much about the permutation, so treat this as kind of beyond the material. Okay, so that's if you had row exchanges. So good, we've seen LU. Stop me if there are questions. So, can you hear me, by the way? It'd be funny if maybe I've been on mute for the last 20 minutes. So Guang Sen is asking, what is AS here? So AS was a different matrix. It wasn't the matrix A, it was a matrix A with rows changed. So I purposely took a matrix A with rows changed because when I created this example, when I was preparing for class, I didn't want to start with this permutation. So what I did is I actually solved it for a matrix like this. Maybe it had the rows in different order. And then I saw, oh, LU decomposition wants to do this permutation. So then I permuted the entries so the first go of LU would not have the permutation. Okay. I hope that's clear. Okay, thanks. Okay. So what do we do with LU? Okay, so we're going to do three things. Let's actually start with not with the core most important thing, which is solving a system of linear equations. Let's actually start with determinants. Okay, so how to compute debt using A equals LU. So ignore the P, okay? Maybe we'll get to the P in a second. Okay. So how to compute the determinant using A equals LU. So do you remember what's a determinant of A? Well, it's a determinant of LU. And what's a determinant of the product? What's a determinant of a product? It's a product of the determinants. And what's the determinant of an upper triangular or lower triangular matrix? It's just the product of the diagonals. So upper triangulars and lower triangulars are easy, right? It's multiply the pivots. Right. Exactly. Right. So what I said is multiply the pivots. So you actually call the resulting entries in the U the pivots. Okay, the resulting diagonal entries of the U are the pivots. Perfect. So let's go back for original A. We've got our matrix A. Okay, and then we'll do L comma U equals A. No, equals LUA. And let's compute the, let's take the diagonal. I think that would work. So wait, diag of U. Diag of U are these 4 pivots. These are the pivots, okay, the pivots. Okay. And let's take their product. So let's do multiply the diag of U. Okay, so this is times applied to the diag of U. That's a product of the pivot. Oh, come on, come on. Why are you saying that? Let's do this. No, I thought this will work. Hold on. No. No, that doesn't work. I thought this would work. Okay, so let's do accumulate. Sorry, I just want to multiply 4 numbers. Accumulate times on diag of U. Is this going to work? Yeah, that's bad. Okay, so I don't know how to multiply the 4 entries of a matrix, but I'm going to write a loop. I'll do for I in 1, 2 length of diag of U, and then I'll do P prod equals times equals diag of U. All right, this is of course extremely inefficient. It would have been better to get the diag of U, or pivots equals diag of U. Okay. This is the length of the pivots. We obviously had 4 pivots. Pivots is to that. And what am I going to prod? What should I initialize this? What entry should I initialize this with? 1. Okay. So some of you might be seeing this thing. Some of you are seeing this, and it's obviously what I'm doing. Some of you are saying, "Oh, what is he doing?" What I'm doing is trying to multiply 4 numbers, and the way I thought it's would be easy to do. Somehow at this moment it's not. And then, you know, the product is this. So let's do the determinant of A. Okay, good. So we multiply the pivots, we get the determinant. We multiply U. But of course, remember our thing was P equals AU. Okay. Now the nice thing about a permutation matrix is, I'll write here, but what if P is not the identity? So the determinant of permutation matrices, I'm not going to get to this now, but it's either positive 1 or negative 1. So depending if you have an odd number or an even number or an odd number of flips when you're doing the permutations. Okay. So all I want to say is that you'll put in front of this product another index if the permutation was not the identity. But again, we're not going to focus on these permutations. Okay, so that's all I want to say about computing the determinant using LU decomposition. But let's now get to the heavier lifting. So the heavier lifting is the system of equations, of course, which is what we are here for today. AX equals B. Now, of course, let's say, why do I want AX equals B? Well, in so many applications, we want AX equals B. And actually, in most of this course, we won't be able to solve AX equals B exactly, and we'll do least squares. That's going to be the bigger thing. But we're looking at AX equals B. So here's the plan. Here's how we're going to solve AX equals B using LU factorization. We will factor A. That's actually the expensive operation. Factorization is always kind of the more expensive, so it actually takes n cubed operation. So this Gaussian elimination, the complexity of it for an n by n matrix is of the order of n to the power 3. Okay, and we'll get our L and U. Okay, and then we'll treat this UX as just some other vector y. Okay, so we'll treat it as an intermediate vector y. And we have the system of equations Ly equals B. Ly equals B. Now, what's easier? AX equals B or Ly equals B? What's easier? AX equals B or Ly equals B? Ly equals B. So why is it easier? Thanks for writing that, Jane. Zane? Bye. So it's easier because L is lower triangular. It's a triangular matrix. Okay. So for a triangular matrix, we actually were going to use just back substitution, and I actually want us to just implement this together because this is kind of the central thing. Okay. So back substitution is what I'm going to scroll all the way up to the top of the notebook, is what we did here after we got to this thing. So then we did back substitution. We solved for y. This is now y, the scalar. And then we solved for x, the scalar. Okay, so when you have your triangular matrices, solving triangular matrix system of equations is much simpler. Okay, let's go all the way back down. Okay. So then after we've solved Ly equals B, we know what y is, but we still have y is ux. We still have this system of equations. Ux equals y. So we again solve the system of equations that's with a triangular, in this case, an upper triangular matrix. And then we finally get our x. Okay. So this might seem like a painful thing. But the thing is that the complexity of Ly equals B and Ux equals B is less than the complexity of solving Ax equals B. Now, it's true that the complexity of solving Ax equals B is like doing the LU decomposition, but look, what if we now wanted to solve Ax equals B1 and Ax equals B2 and Ax equals B3? So we keep the matrix A, but we change the right-hand side. Yeah, so we keep the matrix A, but we change the right-hand side. So how many times do we need to carry out LU decomposition? If we keep the matrix A, but we change B. Did the LU decomposition just once, right? The LU decomposition did not depend on the right-hand side B. Okay, so that's kind of a strength. Now, just to see this strength, before we get to this program of just solving a system of equations, let's go to a third use of LU decomposition, which is finding the inverse of a matrix. Okay. So when you find the inverse of a matrix, you're actually solving more than one system of equations. You're solving n system of equations in a sense. Okay, so let me show you that. Okay. Back. And I think you can see iPad. So finding A inverse. So what's the definition of A inverse? Well, A inverse times A equals identity. Okay, but also we can write A times A inverse equals identity. We proved last week that it's the same. That if you have a left inverse, then you have a right, and if you have a left inverse and you have a right inverse, it must be the same inverse. Okay. So we now want to find this guy. Whoops, it's not what I wanted. This guy. Okay. So let me just write it for simplicity in a 3x3 system of equations. So, and I'll put x, x, x. Now these x's are like stars. They're not even entries. They're just the entries of the matrix A. Okay. And here we have the matrix A inverse, which we don't know. Okay, question mark, 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 equals 1, 0, 0, 0, 1, 1, like that. Okay. So how many system of equations do we have here when we're solving? Well, you might have learned mechanistically, you might have done this in some previous linear algebra course or something like that. What you would have done is you'd said, well, instead of calling this just a right-hand vector b, right, because it's not ax equals b. Now it's a times something equals something, okay? So what you would have done is you maybe did in Gaussian elimination, you put the matrix A here and you put the matrix I, and then you did the row operations on all of them together, and it was like transformed to A tilde and to I tilde. And you did the next step and it was A tilde tilde, I tilde tilde, etc. And you did this until you ended up with the I, and then I tilde 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 tilde. You did many operations, and then you would say, ah, this is my inverse. That's how it's kind of sometimes taught. Now, what you're doing here basically is you're taking the matrix A, this matrix A, you're multiplying it by this vector. Okay, so this is now the way 2 of matrix multiplication. So in that first lecture, when we had the multiple ways of matrix multiplication, it's important. So this way 2 of matrix multiplication means that the matrix A times this vector is this vector. And the matrix, let me do a different color. So the matrix A times this vector is this vector, okay? And the matrix A times this vector is this vector, okay? And that's basically what you're doing. So in all these cases, it's like solving, it's like you're doing AX equals B, but each time your B is a different unit vector. So the word unit vector, I don't think I've used here, but we're going to use it now a lot more. So B is sometimes going to be the unit vector E1, which is 1, 0, 0. Sometimes it will be the unit vector E2, which is 0, 1, 0. And sometimes it will be the unit vector E3, which is 0, 0, 1. These are unit vectors. Okay. Sometimes people just write E like that and they mean that's what we mean, like a bold one, like a vector of ones. I don't like that notation so much, but it's sometimes done, just so you know. Okay. But if you have an E with a subscript, it's a unit vector. Now, of course, if I just come to you out of the blue and I tell you E7, I'm just speaking for a second about unit vectors, E7. I mean, do you know what's E7? You can't tell me. You don't know. You don't know because you don't know if E7 is 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, and that's it. Or maybe it's E7 in the space of like 11-dimensional vectors. Okay, so I need to tell you in what space of vectors I'm speaking about. Okay, just that was a discussion on the unit vectors. So basically, when we're computing the inverse, we want to compute AX equals B for different values. So if you had now an LU decomposition, if you knew, I'm now going back to LU, if you knew that A equals LU, and I'll put here a little very thin purple P, you know, maybe a P, but just ignore that P, okay? Okay, just ignore it for now because we just don't want to speak about that. Okay, so if you do that, then you can now do LU X equals E1, LU X equals E2, LU X equals E3, or etc. up to LU X equals EN. And each time you would then use this to find X, you know, let me call this X1 and X2, X3 up to Xn. And then A inverse is going to be the X1, X2 up to Xn. Ran out of space. Okay, I hope that's clear. right? So it's repeating the problem of solving a system of equations, but you've already you only needed to factor your matrix once. Okay. Now, just to make order for those of you that have computed inverses in this way, well, here again, I mean, you do the same row operations again and again, and the matrix L encodes these row operations. Okay. So we're actually not going to do this a whole lot, but I just wanted you to see that. Let me go back to desktop, because I want us to focus on actually just solving a single system of equations. And for this, we're now going to deal with back substitution. Okay, we're going to deal with back substitution. So I'm referring here to algorithm 11.1 in page 207 of VMLS. So VMLS is really, in a sense, VMLS doesn't cover everything we need in this course, but it covers a lot. And it's you have a homework assignment from VMLS. Now, some of you have noticed that the homework assignment for VMLS requires you to read a bit in VMLS to actually see definitions of correlation and things like that. Let me stop the share and go to share screen. I think this will work now. Okay. Just my chat has disappeared. Hold on. So what? You know what? Let me just try and adjust things a second. So what I'll do, I'll just go to the book from the course website, just because it's easier to see it on the browser as opposed to PDF. Okay. So I actually want us to implement this just so you see how easy it is, and also as another exercise kind of together. Am I doing this because of time? No, we still have enough time for what we wanted to cover today. Now my chat has also disappeared, sorry. Whenever I switch devices, there's some issues. Okay, there we go. So page 211. Sometimes the page numbering in the PDF is not the page numbering in the book. So just because there's some front matter. So there we go. Here's an algorithm. The algorithm is called back substitution. Now, when we get to, if you read around this in this book, one of the things I like about it, it doesn't actually speak about Gaussian elimination at all. I mean, who would have thought a course in linear algebra with Gaussian elimination? And thus it doesn't speak about the LU decomposition. It actually goes immediately to the QR decomposition that we'll speak about in a few weeks. But both QR and LU decomposition, I might as well show you now very, very briefly. So both QR, and we didn't speak about QR decomposition, okay? So both LU and QR decompositions are of the form A equals something times an upper triangular matrix, okay? Where U is upper triangular. Okay? It's just that in QR, this something is a Q, and it's what's called an orthogonal matrix. And in L, which is a matrix such that its columns are orthogonal to each other. So the inner product of different columns is the identity if it's the same column, or zero if it's different columns. We'll get to that, okay? Whereas with LU, it's lower triangular, okay? But in both of these cases, after you represent A like this, then when you want to solve a system of equations with a decomposition, then what you're ending up with is a system of equations like this, okay? So this R in this book, look at the system of equations here. This R is like our matrix U for our case, okay? But this is the R from QR. Oh, Robert suggests try exiting full screen mode. I'm not sure I'm in full screen mode. I'll leave it for now if it works, all right? But thanks for the tip. Okay. I mean, I somehow, because I'm working with two screens, changing, blah, blah, blah. All right. So look at the system of equations. R11 times x1, x1 is a scalar, plus R12 times x2, plus R1n minus 1, the n minus 1 from times the penultimate variable, penultimate is 1 before last, times R1n times xn, okay? And then here comes the second row, but this second row doesn't have R11, it has n minus 2 to n minus 2. Okay, so it goes, you don't see here the second row. The second row would be R22, etc. But you see, these are always, this is basically what I want to do here. So I just scratch on this like this. This is a form of a matrix which is upper triangular. In this case, yeah, that's a matrix R times the vector X equals B. Okay. And we're guaranteed that the entries in the diagonal are not 0. Okay. So all you need to do for back substitution, here's now the algorithm, and here's the algorithm. Given an n by n upper triangular matrix R with non-zero diagonal entries, okay, and some vector B, so you just loop I going from n to 1, you loop from the end, and you read out the xi's one by one like that, okay? So this is the last equation, the second to last equation, etc. So let's just code that. Let's just code that directly. Okay. So we're going to make, because this is what we needed to do basically here, only that with L was lower triangular and U was upper triangular. So let's have that victory together. Okay. We still haven't solved the system of equations. Right. So what we do, we want to make a function, and that function is, maybe we'll call it solve upper triangular. Okay. So let's call that matrix R. Okay. Or you know what? Just to be clear, let's call it the matrix U in our case. Okay. And let's call B the right-hand side. Okay. And I'm not going to do too much documentation or assumption or error checking now. I'm just going to see that it works. Okay. So X, I mean, we need one dimension. We need N is like the size of U, say the first entry. Okay. So, you know, U is assumed to be an n by n square upper triangular matrix, and B is assumed to be a vector. Okay. And the entries of U in the diagonal are assumed to be non-zero. Okay. And then let's initialize our vector X. X is going to be the solution. Let's just initialize it with 0 of length n. And now we'll do a loop, and we'll do it just like VMLS suggested. Okay. So we're going to go, I will go from n to 1. So let's just do that. For I in n to 1. And then what we're going to say is, we're going to say the ith coordinate, so x at the point I, okay, is going to be b at the point I, right? This is as bi, minus this thing, okay, minus this summation. So what is the summation? This is all of the x's that we've had before times the matrix R. So it's basically, I'll draw on here. It's, if we're now working on the, well, let me draw in a different color. If we're now working on the coordinate here, say, is this working? Sorry. If we're working on the coordinate here, so we've already solved all these coordinates here below, okay? So now we're going to use our solution, and we're going to multiply them by that. So this is this guy, okay? All divided by RII. Let's just do it. Sorry, let me erase all the drawings here. Okay, so what we're going to do is we're going to say xi is bi minus, let's just call this the product. Okay, we'll compute this one row below before that, divided by, just like said here, RII. RII. Okay, and in the end, we're going to return the vector x. So what we need to do is we now want to compute this product. Okay. So this product, we know about inner product, so let's just treat it as an inner product of two things. What is it going to be? It's going to be an inner product of two things. It's going to be an inner product of all of the x's that we've solved to date. So we're now in the ith iteration. So we've done x from, you see, from I plus 1 to n. So from I plus 1 to n. So that's this vector x. Let's do an inner product like that with a c dot. You could have used a dash or a dot or whatever. C dot. Okay, let me just, so it's clear, and I'll just do a dot. Okay, an inner product of that. Times the r's. Okay, so we're now looking at r's in the ith row. And again, we want to take their index, see the ith row, I is the same here, the same, index I plus 1 to n. Okay, that's it. And that's it. That's how we'd solve an upper triangular system of equations. Now, I'm actually not sure if this will work. Oh, okay, thanks. And this one is correcting me. This shouldn't be an R, this should be a U. Thank you. U and a U. See if the group of us can find any other typos. Now, I'm not sure this will work because when in the first iteration, I equals n, and then we're doing like dot from n plus 1 to n. So it's like dot of the empty ones. Okay, so that, and Rob was saying, so on first iteration I equals n, we have n plus 1. So I'm not sure that the dot, we might need to do like, you know, kind of fix the first iteration. So let's see. You see, so maybe there's a problem with first iteration, but maybe Julia's smart enough and they'll take like empty vectors and they'll say dot of nothing and nothing is nothing. Let's see. So let's just, and to test this before, let's just take a system of, let's just take a matrix U. Let's take the same one we had up here, which is 1, -2, and 8. And 1 and 8. Remember this? 1, -2, and 8, 1 and 8. Let's go all the way down. I hope I can remember it. 1, -2, 0, and 8. And let's take B to be 1 and 8. I hope that should be okay. And now we can do solve upper triangular. UB. We get 0, 0. That doesn't look good at all. 1, -2, 0, 8. Solve upper triangular UB. Xi equals bi minus the prod. Okay, so that doesn't look good. So now let's see what went wrong. What went wrong? First of all, let me just do. Yeah, are we in the right one? I think so. Solve upper triangular. Okay, why is it 0, 0? So let's think before we look further. So let's actually just show the prod. Min of I plus 1 and n. So yeah, I think no. So the vectors are row vectors. Well, the vectors are column vectors. I mean, these are each kind of, when you take a splice of a matrix, it's like a column vector. Let me, I put here a show prod in line 6, and I'll run this again. Oh. For I and n, oh, I see. You see, okay, so now I did show prod, and I ran this, and it printed nothing. So I think that this loop never happens. Println, hey man, I am here. Let's, you know, run this again here. It never prints, hey man, I am here. So what we need here is n minus 1 like that. You see? So this range needs to go like with steps of negative. Okay, n minus 1. I think that, let's run this, it'll do a few hey mans. Okay, hey man, I'm here, I'm here, and it solves something. So let me now comment this hey man, comment this show. So keep this in mind. I mean, if you're debugging stuff, blah, blah, blah. And we get a 3 and a 1, and I think that's supposed to be the solution, right? So that was the solution we had before. Okay. For here was a 3 and a 1. Okay, it seemed to work on this 2 by 2. Now, this is almost all we need to use LU factorization for our recipe for solving a system of equations using LU. We had AX equals B, LU equals B. We had now this system of equations. The first one was actually a lower triangular matrix. So that's actually not going to work. This is what we have for the second system of equations, the upper triangular. So this was a function that we called solve upper tri. Okay, so might as well let's now do another function that we'll call solve lower tri. Okay, there are different ways to do this because it's effectively the same algorithm, but you just need to kind of flip the thing. So lower tri, L of B. But let's just use a reasoning. N is going to be the size, fine. X is still going to be the zeros. How are we going to make our first loop now? We're not going to loop from, so just think otherwise. Before you thought upper triangular, now think lower triangular. What are we going to loop? Not from N to 1, but from, if we're doing now a lower triangular, from 1 to N. It's like easier, right? It's more sensible. Good, thanks. I'm going to do 1 to N. Now this product is just going to be from 1 to I. I think it might be 1 to I minus 1. Yeah, I think it's 1 to I minus 1. And it's going to be the empty set. 1 to I minus 1. I think that's the case. Let's think about it in a second. And this should be the same thing. Let's see. So we're thinking now of a lower triangular system of equations. Let's see if we can think about it. It's a bit complicated. So we've got a system of equations. These are the non-zero entries. This is the X. Here is like zeros. Yeah, all this place I'm scratching is zeros. And this is going to be the vector B. Right? This is B. This is X. And this is L. So the first iteration, I, is 1. Okay, so all we need is B of 1 divided by U11. That's how you get this first entry here. Okay, so this product needs to be nothing. So we actually, you don't care. There was nothing before. It's like from 1 to I minus 1. I think it's okay. And except for the L's, I'm going a bit quick. For the, what should I change in line 5 and 6? We have a matrix L. Okay. To see that this guy works, let's just invent something. Let's just call the matrix LL. Let's call it 2, 0. Let's do a 3 by 3 in this time. Okay. 3, 1, 2, 0. 1, 1, 3. Okay. And let's call B just a vector 1, 1, 2, for example. Okay. So if I want to solve LL slash B, this is going to be my solution using not knowing that this is lower triangular system of equations. Let's call this X. Okay. Let's just check. I'm first just checking my example. I'm doing LL times X minus B should be 0. Okay. This is how we used it using backslash. Okay. By the way, in Julia, backslash, if your matrix is lower triangular, Julia knows it's lower triangular if it's tagged as lower triangular. And then the backslash will be this much more efficient algorithm. Which algorithm? The one we just implemented. As opposed to doing LU factorization or Gaussian elimination or something like that. Okay, so now let's do solve lower tri. of, oh, and let's just, oh, this is our B. This is 0.5, da, 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 da. Solve lower try LLB. That didn't work at all. 0.5, this is 0. So 0.5 worked, but the next one didn't work. You see, so this entry here, this 0 should have been a minus 0.25. So what are we doing wrong? Should line B be I, 5B, L from I, oh, yes, L, I. Well spotted. Well, okay, just like before, it was R. I mean, we have to go to the ith row. You know, it was the ith row. Yes, very good. Very, very good. I mean, 50 people can code together much better than a single person. So we think, let's see, solve lower try. Yeah, very, very bad, very bad. Not good at all. Not good at all. So we got an error. First array has length I, which does not match the second array. Okay, so come on, let's not butcher this. So no, this needs to go the elf I from, oh, come on. I, comma, like that. Okay, it wasn't even true. So L from I, the ith row, from 1 to I minus 1. The length of this vector is in the same way. Yes, okay, new standard. Okay. Again, if some of you are seeing this and saying, oh my God, how am I supposed to code so quickly? Not that I'm coding so quickly, but I have your good help. No, you're not. You're not. I mean, this is trying to actually show you that it's not so complicated, and you know, you take a bit of more time and you kind of make it work. And did we make it work? We made it work. Good. Okay. So now we've got 3 minutes. So we know how to solve a lower triangular. We know how to solve an upper triangular. Let's get back to our LU, AX equals B. Okay. So now let's do a function which we'll call using LU to solve it. Okay, A and B. Okay, so, and you know, this function has a lot of assumptions. It assumes that A does not have permutations, etc. And it's not a function you really need to use, but it's just going to show you this whole scheme. Okay, so what we're going to do is we're going to do L comma U equals LU of A. Okay, we're not implementing LU decomposition of A. That we did manually. But we're using the Julia LU decomposition. Okay, but we are implementing the back substitution. So the first thing we need to do is we need to do Y. We need to solve for Y, okay? So Y is lower triangular solve of L and B. Okay, so solve lower try of L and B. It's actually, we'll just copy it just like that. And then we're going to say X is solve upper try of U and what? U and what's the right hand side? It's not B anymore, it's Y. And we don't even need to call that X, that's just a return value. You know, the last thing you put in this function is a return value, I just put return, so it's clear. Okay. So let's see, do we have our matrix A or the original one? This is its original A, I hope. Okay, and do we have a vector B? No, we don't have a vector B. So which B do we take? Let's just take B to be once. Okay. Okay, so let's do the solution using backslash. Xsol is, you know, this happens to be the solution. Just to check, I always like to check to see that everything was okay. So A times Xsol, oh, here's the check. Just the norm of A times Xsol minus B is 0. Okay, so that means that A Xsol equals B. But let's use R using LU to solve it. And we've called the function arguments here just like the global variables a and b, so that's fine. Hey man, I am here. Why is it saying this? I thought we got rid of hey man. But let's just treat it as a feature and not a bug. The fact this thing says amen, and it looks it says 0.1 and 0.1. 0.11, 0.11, 0.26, 9, is that? So it worked. Hope you're feeling proud. I have no idea what is here because we recompiled, but it's maybe a different version of the function. Okay, I don't care. Oh, we just never deleted those. We never recompiled the function. We never did solve lower try again. So let's just do it to see if it works. So I did now shift enter on solve lower try and run this. We still get the commentary, but that's okay. It's just that still exists in a different version of the solve lower try for some reason. That doesn't matter. It's saved. It's saved in solve lower try. Yeah, but here we're recompiling solve lower try, but there might be two. So now, okay, now we're leaving linear algebra. So I can take a break in a second. Oops, no, that's not what I want to do. So if we do methods solve lower try, I guess there's two of them maybe. No, so I'm not sure. I have no idea why it said. Why did it not recompile this function? So shift enter on this. And, oh, okay. It's, so this was saved and using LU to solve it. So you need a, Julia feels like an interpreted language, but it's a compiled language. So when I do here, I need to recompile the function using LU to solve it. And here it is. No, okay, I give up. It's time for a break. It doesn't matter. This is not related to linear algebra. This is kind of a software thing. So we used LU. I hope this kind of long story kind of made sense. The point here is LU, Gaussian elimination, and all of that. Let's take the normal break, just 8 minutes. So see you in 7 p.m. Brisbane time. I'll see you before for questions. So I'll take a 3-minute break and I'll be online. Okay, so Robert is saying the reason is you wrote solve lower try by overriding solve upper try, and the show was implement and solve upper try. You should have rewrite and compile solve upper try. Oh, okay, let's give that a go. I thought that's what I did. Using LU to solve it. Solve lower try. Oh, I just didn't run the same one. Oh, okay. This one we didn't recompile. Thank you. That's all you're saying? Good investigation. Let's see. We don't want hey man, I am here. No hey man. Thank you. I've got a different question for you. So this thing. Question number one for the audience. Is this Mandarin or Cantonese or some other language? This is. Can somebody read this? Am I on? It's Mandarin. Yeah. So yes, thanks. Okay. Now, so my daughters are addicted to bubble tea. So this has made kind of big impact and bought this. And my big question is, does this have caffeine? Does this have caffeine? Caffeine. Does it have caffeine? So I didn't want to let one of the daughters have it last night. It contains tea. So, oh, no caffeine. No caffeine? No, it has. Oh, we have disagreement in the class. Yes, caffeine or no caffeine? I mean, tea, my view, so then I read the back here. The back kind of has nutritional information that's in English. And it didn't say no caffeine. Oh, this is product of Taiwan. Okay. And I figured if they don't say no caffeine, so yes caffeine, right? So that's a consensus. That's what Tian says. If it contains tea, it may have, it has. Yeah. Thank you. Because tea has it. Yep. And unless it's kind of special tea without caffeine, right? But then they would have said. But tea, yep. Okay. Any questions now that you've helped me with this parenting issue? We'll start in a minute. So we're done with the LU story. And I think one thing you're seeing here is that a lot of these things that you do, of course, in a quiz situation, you're not able to check yourself often, but in a non-quiz situation, you can just check, you know, you solve the system of equations, you check, you do the factorization, you check, you do all these checks all the time. Okay, 7 p.m. in Brisbane. Let's move to the next thing. So I'll quickly show you the quiz, which is an example of what quiz one can look like. You have this in the GitHub, okay? So we'll just read this and see how you'd solve this. Okay, we won't solve it per se. Yeah, so there's a question, are there a difference between LU and QR? Yes, huge difference. So QR is a factorization which we haven't studied yet, where the matrix Q is an orthogonal matrix. It's not a lower triangular matrix, okay? It's an orthogonal matrix. We'll speak about that in a week and a half, okay? LU is what we've just done. In both of them, the right-hand matrix is upper triangular. Okay. Both of them can be used to solve system of equations. QR we like more because it also helps least squares. I mean, but LU is very big as well. Okay, so say you're given an LU factorization matrix A, and this is L and this is U. Okay, so say you're giving that, and A equals LU. So this line here tells you that there's no P. There's no PA equals LU. So you know there's no permutations. A, how do you solve A? Find the matrix A. I mean, this is kind of the level of the quiz is to see that you can speak the language without the language of mathematics, linear algebra, without help, except for your formula sheet, which is part of your preparation. But how would you find the matrix A? Nothing to do. L times U. You do matrix multiplication. So you find matrix A. That's it. 10 points. Okay. Use factorization to compute the determinant of A. How would you compute? Of course, you can compute the determinant of A based on your answer in A and do a 3x3 determinant. But how would you use it? What's the determinant of A? Just tell me the answer numerically. What's the determinant of A? Minus 16. So it's a product of the pivots 4 and 2 and minus 2, which is minus 16. Perfect. Use a factorization to solve for x in ax equals 1. Now, if you're in the quiz next week and you see this 1 and I didn't write what 1 is, I'm actually in the quiz. I'm like, you'll see my face like this. Like that. So you can ask me. Okay, I mean, it's like a class quiz. You don't have to turn on your camera, but I'm with my camera pretty much on, unless I go and grab a snack, make myself tea maybe. So 1 is a vector of ones, okay? 1, 1, 1, so the right-hand side of that. So now you use a factorization. So this is kind of a bit of work, but it's not so much work, because what you'll do is you'll have L and U, so you'll first solve, just like we did. You'll solve L y equals 1, so you'll solve for y, and then you'll solve the other one, just like we did. Okay. D, use a factorization to find the inverse of A. So here you'll do this 3 times with a different right-hand side, and you'll find the inverse. Okay. And this is maybe a bit too long. Like I wouldn't give, that can be almost a bit too long to do, because that's quite a lot of computations. And E, use a factorization to find a different factorization. A equals L times D times U, where D is a diagonal matrix, L is lower triangular with ones on the diagonal, and U is a different U now, upper triangular with ones on the diagonal. So look, LU is kind of not fair, because you see L is like, I've got ones on the diagonal, but U doesn't. So what you can do is you can squish another matrix in the middle, and it's a matrix D, and that matrix will just have the pivots, 4 and 2 and -2. And here you'll divide U by 4 and 2 and -2, divide the rows by 4, 2, -2 respectively, and that's called the LDU factorization. That's all. So you just need to write what that matrix D is. Okay, E is kind of slightly harder if you've never seen the LDU factorization. I more put this so you see this is roughly what a quiz looks like. Okay, this is not the quiz. Okay, and then question 2 is about these things, which we're going to speak about now. Questions about this? Okay, so the next thing is we're going to speak about now a completely different subject, which has to do actually with calculus, with continuous functions, but it sort of falls in the same realm of the introduction to this course. Now, but before that, very quickly, there's just some things here that you saw in the tutorial, in the practical as well, with this RF function. So you've seen this in the practical. So what RF does, it can take a matrix A, and it does not just Gaussian elimination, it does Gauss-Jordan. So it also then applies Gaussian elimination downwards, and then it's like applying Gaussian elimination again on the matrix U toward going up, okay? And here's like one way, a different way to compute the inverse with that. So say you have the matrix A and you have the matrix I. So you want the inverse of A. So here's a 1, -2, 3, 2. and here is I, so that's AI. And if you do this RF, this is called row reduced echelon form. You apply to AI, then you get here the inverse. Okay, so this is like this original, this other system I showed for finding the inverse. You see, that's the inverse of A. Inverse of A is the same, and like this, it's this row reduced echelon form in the columns 3 and 4, etc. This is not numerically used, and that's why it's actually in a different package, row echelon. Okay, so it's kind of a package. It's more just used for education purposes. You can go to row echelon JL. This is actually the source of the package. Okay, and if you, sorry, in GitHub, okay, you can give them a star, poor guys. This is like a good thing to have, because MATLAB has this built in, but in Julia it's like this kind of added in. And just you see something nice about Julia, this is actually, this is actually how they implement this function, RF, okay? So, you know, there's some logic and some loops, etc. But this is doing Gaussian elimination. Now there's a few more issues here that kind of make it this union and stuff like that. So it's the type, are you working with rational numbers or with integer numbers, and a few questions of that type. So that's why the code is more kind of industrial. But if anybody wants to actually have a look, you don't have to, yeah. But this is actually how this Gaussian elimination is carried out. Again, this is not the heavy duty industrial Gaussian elimination, which is carried by LAPAC. But that's this RF function. So I'm speaking about this very quickly because we're going to speak about these other issues related to it when we speak about vector spaces. That would be the week after next week. So next week we have the quiz, and then I'll teach just a bit more after the quiz. So an important thing of a matrix is the rank, and that's the number of pivots in the matrix. Okay, so which is basically the number of linearly independent columns and the number of linearly independent rows. But we'll speak about this more next week, or when we speak about that the week after probably. Okay. Yada, yada, yada. And that's all I wanted to say about this. And now we're moving to something completely different. Okay. I hope you don't mind. I went very fast on this. Any questions? I mean, in general? All right. Okay, so Shelfie asks, can we use Gauss-Jordan elimination if the question asks to use Gauss elimination? Yeah, you can. You can. I mean, I'll know that that's what some people want to do. So I'll be more specific if needed. But anyway, you can position to me questions during the quiz if something's not clear and what we can do. Okay. All right. So now we're speaking about something completely different. Now, for the few of you that did not do MATH7501 or have never studied stuff like MATH7501, then I hope that at this time you're still going to the course suggestions on what to study back in MATH7501, etc., etc. And one of those things is this concept of a Taylor series. So this is now, we're leaving linear algebra for just a second, okay? And we're speaking about a Taylor series. So a Taylor series is an approximation of a function using a polynomial, and the approximation is a local approximation. And we spend time speaking about that in MATH7501. So if you go to the MATH75, I'll go to MATH7502. Go to the courses. Google still thinks we're in 2019. That's okay. We'll go to 220. And then you go to the background info here and the MATH7501 course reader. Okay. And if you go to this section, linear approximation Taylor series. So there was Taylor series in one variable. Okay. That's a Taylor series. So have a look at that if you haven't dealt with Taylor series for a while. But that's only background info, because what I'm going to speak about here is kind of straightforward, and we're not going to get into it very deeply, but it's important because it connects kind of the non-linear world of smooth continuous functions that are non-linear to linear algebra, and will kind of reappear in the course several times. So the first thing I want to speak about is a function that goes from Rn to R. Okay, and this is like, this guy is so common in data science and in machine learning. Okay, so Rn can be your parameters, and R here is going to be your loss. So sometimes it's a loss function, so you're trying to minimize loss, or you're trying to get the best fit. So that function kind of measures how good the fit is, and the data is often fixed as you do that. Okay, that's kind of very vaguely the situation. Okay, you know, but this is any function that goes from Rn to R. I mean, you had in the first week with Sam and Walla, you plotted such a function from R2 to R. So this is MATH7502 material. This is a vector. What do we call this vector? What do we call this vector? This nabla, this inverse triangle, this opposite triangle. What is this vector called? It's a gradient vector. Thank you. It's a gradient vector. So what this vector tells you is it's taking now partial derivatives of this function with respect to the variables x1, x2, up to the nth variable. And it's computing the value of those partial derivatives at some point z, and the gradient vector basically points in the direction of steepest ascent. Okay, so again, if you go to Math7501 course reader, you actually have here partial derivatives and gradient. Okay, all right, and for example, the algorithm that's really kind of pushed AI further, even though it's a very simple algorithm, gradient descent is kind of based on going in the direction that's opposing in the direction of minus the square. So what we're going to do is we're going to say this gradient can be part of a first order Taylor series approximation. So you don't need to worry about a higher order terms in this specific course. You just worry about the first order terms. And this is how it goes. So your function could be a rather complicated function. So what you're going to do is you're going to look at the function. Let me zoom in just a bit. You're going to look at the function at the, and you call this f hat. And you'll say, what is f hat of x? Well, f hat of x is just going to be an approximation around the point z. So it's an approximation around the point z. Z is like a fixed vector. Okay, z is a fixed vector in n-dimensional space. Okay. This, by the way, it's all in the VMLS book in Appendix C. Okay, so, and what you're going to do is you're going to say it's going to be the partial derivative of this function with respect to x1 at the point z times the difference between the first coordinate of x and the first coordinate of z, plus the partial derivative of the second coordinate times that difference, etc., up to the last one. Okay, this is what this is going to be. Now, the nice thing is we already know about inner products. So we can write this very neatly just in terms of an inner product. And here it is. Here it is. F hat x. And here, by the way, I should have had this too. F hat semicolon z. That semicolon kind of says it's with respect to the point z. Okay? Is f of z plus the inner product of the gradient and the difference between the point x and the point z. Okay. So this is what this function here is, it's an affine function of x. It's called an affine function of x. And the point x is anything. The point x is anything. So it's like, let me now draw for a second contours. Let's see if I can draw like, this is like contours of a function. Okay, so here's some contours. So think now, I'm drawing like a a two-dimensional function, so this R2, okay? So what you see is contour lines of this function. So let's say I'm taking this, let me change color. I'm taking, say, this point here as a point Z, okay? What I'm doing now is I'm taking a plane, which is, well, it's hard to do, but it's hard to draw. But this plane is touching the function exactly at that point, okay, that point Z, and I can pick any x that I want. I can pick x to be this point. Whoops, let me draw this. I can pick x to be this, or I can pick x to be here. Okay, I can pick x to be here. And every time I will care about the distance from x to z. This is the difference between, well, it's not the distance, it's a difference. And I'll take the inner product of that with the gradient vector. And this is where I'm going to be on this hyperplane that's approximating the function. So that's a Taylor series approximation of such a function. Okay. Now, if I happen to put, what if x was z? What if x was z? Is my when is my approximation most exact? I should have asked this like that. The approximation is perfect when x equals z, because then I just have f of z, because x equals z, because this thing is then 0. Okay, sorry, I've done too much drawing on this. Okay, so that's the Taylor series approximation to a function, the first order approximation to a function. And we use it because it converts something that's potentially nonlinear, you'll see an example in a few minutes, into something linear, okay? But that approximation is only good in the local vicinity of Z, okay? So yeah, that's it. Okay, now one can work a whole lot with these and do some things, but we're already moving to the next one, okay? So moving here to a function with the domain is still Rn, but now it's no longer a scalar value. This m here, it's not necessarily a scalar n. It's m-dimensional space. Okay? So sometimes people would call this a mapping. I mean, it's still a function, but it's a mapping. It takes vectors in Rn and then puts them in Rm. Maybe m equals n, maybe m is smaller than n, maybe m is greater than n. Okay, but it's going from vectors from one space to a different space. Now, in this case, what we can do is we can represent f of x, okay, and this is an element of Rm, okay, as m different functions. There's m different functions. Here's the first function, as m different scalar functions. Here's the first function, here would be the second one, and here would be the mth one. So we have m different functions, okay? Where each of those functions, each function f sub I is a mapping from Rn, because the domain is n-dimensional, Rn, to the reals, to R1. Okay, so it's basically taking like the function we had before, but you've got now m of them. Okay. Now, when you deal with such a mapping, and we'll have examples later on a bit related to the normal distribution, but this is also related sometimes to dynamics and robotics, and we're certainly not going to deal with these such things. But when we deal with this, so I'm kind of quickly going through this. When we deal with this, you have a matrix which you denote like this. This is a notation, this D, and that's called the Jacobian, okay? Like Jacobian, that's a person, okay? And that matrix, it's an M by N matrix, okay? And the ijth entry, so I, the row I and column J, is the partial derivative of the ith function with respect to the jth variable. I know it's a mouthful. At the point Z, at the point Z. So that's a Jacobian at the point Z. So Jacobian generalizes the gradient. Okay, so this is now going to m-dimensional. Again, this is all in the VMLS Appendix C. Okay. Even though it looks complicated, you'll see there's not a whole lot to compute here. We'll actually compute an exercise. So the Jacobian generalizes the gradient. Okay, now the rows, if you look at it a bit, etc., are nothing but the transpose of the gradient vectors, the ith gradient vector. So like the first row is the, so this is just a function. This f1 is going from Rn to R1, and the gradient vector of that, you transpose it. Okay. And the nice thing about this is you can now, again, do a Taylor approximation. Okay. And let me again do this kind of same type of notation. Blah, 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 blah. Maybe z like that. Is that what we want? Yeah. So you can take some point z. Z is now a point in n-dimensional space. Okay. And I can approximate the actual function by a function f hat, which is again going to be a linear transformation. It's again going to be a linear transformation. You'll see this in a second. So now the ith coordinate of this function is just going to be the ith function at the point z, plus all these partial derivatives. So it's nothing but this the same type of approximation we had before. It's fiz plus the inner product of the gradient vector of the ith component of this mapping times x minus z. So this is a fi, and I goes from 1 to n. So if I put this all together, let me again put this semicolon here. Sorry for that. Then you get, this is kind of one of the nice things about math. You kind of have all these small details inside, but then you get this beautiful formula. So what it is the first order approximation of this function. And it needs, you know, it needs to have derivatives. It needs some functions, as you might remember, are not differentiable, like absolute value at 0, not differentiable, etc. It needs to have derivatives that's said it is smooth, okay? It's certainly continuous. It's differentiable at a point, it's continuous at that point. But let's leave that. We're not speaking that level of detail here. So the approximation is going to be the around the point z is going to be the function value at the point z plus the Jacobian matrix times the difference between the 2 points. Now, I know I threw now a whole bunch of things at you, like blah, 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 blah. A lot of things. But the point is here that now you've got a formula that looks like for any given z, when you fix z, this formula is of the form f of x. I'm writing on the laptop with a pad, so it's a bit nasty, is some constant, let me call this b, okay, plus some matrix A. This doesn't have to do with the A and B system of equations that we had, although it can be related to that, times x, the vector x, minus the vector z. Okay, where A and B here depend on the z. Okay, A and B depend on the z. Okay, but you see, you basically have a matrix A and a vector B. So what this kind of, at least from bird's eye view, it can give you a feeling how matrix algebra can fit in this world of smooth functions or continuous, smooth continuous functions using this kind of Taylor approximation. Okay, so that's it. We're not going to do a whole lot with it, but I actually purposefully, I don't think, I'm not saying if it's going to be on quiz 1 or not, but we're now going to do this question 2, just step by step, which is like potentially a quiz question. Okay, so that's an example. And that's how we'll spend the rest of our time now. Okay, we might get to linear transformations today, maybe not. So what I'm going to do is I'm going to share the iPad again. And we'll work on this question. Are there questions? I bombarded you, blah, 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 blah. No? Okay. So let's see. All right. So I think what I need to do now, sorry, I should have had this on the iPad, but I don't. So I'll just write the question. So, so this is question 2 from the, I don't want to even call it a practice quiz. It's an example quiz. What you need to do for preparing for the quiz, you need to go over the material. You need to make your cheat sheet that summarizes all of these things. And that's kind of the learning process. And with the exception of doing the homework, there's not a lot to do. You can maybe do a few exercises from the book if you really have time, or from the books at the level that you see here. You can also look at, no, that's pretty much it. Okay, so we have a function from R2 to R3. Just to be clear, this is a function that takes points in the plane. This is like the plane, and puts them in space, okay? Can you give me like a, some function where this, you know, yeah, okay, let's not have an example. Okay, so it's a mapping that takes each point in the plane and puts it here in space. Okay, and here's how this mapping works. So it's, I'm now copying from the quiz. It's fxy. Now when I write fxy, it's like abusive notation because it's basically f of the vector, and that vector is like xy, right? I mean, that's kind of really what we mean, but we just write fxy. Okay, and it's fxy, and it has as a first coordinate, so I'll call this f1 of xy is x squared times y, and then f2 of xy is e to the power x plus y, and f3 of xy is x times e to the y. Okay, you see? So you give a point x and y, give me the x, give me the y. Oh, battery's low here. And I'll give you the first coordinate, the second coordinate, and the fifth coordinate. Okay, you got these 3 things. All right? All right, so question A. Question A is we're asked to compute, oh, we have some messages. Okay, so question A, we have find the norm of f of 1 comma negative 1. Okay, so what you need to do here is you just need to plug in 1, negative 1. Okay, so let's just do this. Let's just do, it's a square root of this guy. It's 1 squared times negative 1. That's this guy squared. So this squares from the norm. That's the f1 plus e to the 1 plus negative 1 squared plus 1 times e to the negative 1 squared. Okay, and you can simplify this a bit, not so much, and that's going to be the norm. Okay, correct me if I make a mistake, which is possible. Okay, B. B is still not related in any way to this new stuff that you've just learned. Compute the trace of the matrix fxy times fxy transpose. What's fxy? So fxy, so times fxy transpose, the trace of this guy. What do you call this type of matrix? A column times a row? What do you call it? There's a name for it. An outer product. It's an outer product, right? So it's a 3 by 3 matrix, right? So in this outer product, you don't even need to write this outer product. So the trace is going to be xy that squared plus e to the power x plus y squared plus x times e to the y squared. Okay, that's going to be the trace. Okay, and at the point x equals 1, so substitute x equals 1 and y equals 1. Okay, That's going to be the trace. So the third thing is compute the Jacobian matrix. Okay, here we go, Jacobian matrix. All right, so compute the Jacobian. So Jacobian is D of F. Okay, Jacobian matrix. So the Jacobian matrix is going to be a, a 3 by 2 matrix. Okay, so the Jacobian has is going to be a 3 by 2 matrix. Am I correct? I going from 1 to 3. Yes, I'm making a mistake now. Jacobian is going to be a 3 by 2 matrix. Yes. Where here the first entry is going to be the gradient of F1. I'm just not going to write the XY transposed. The second row is going to be the gradient of F2 transposed. Third row is going to be the gradient of F3 transposed. So there we go, that's a Jacobian. Okay, so let's actually write the entries. So let's now make more room. Okay, let's look at the gradient of F1. The gradient of F1. So the gradient of F1 is, so F1 is like a function from R2 to the reals, okay? So the derivative with respect to X, and then derivative with respect to Y, okay? So the derivative with respect to X of, so you see it here, is going to be 2xy, okay? That's the first entry of this gradient. And then the derivative with respect to y is going to be x squared. Going to be x squared. Okay. Again, high chance I can make a mistake at some point. Correct me if I'm wrong. The second gradient is with respect to the second component function, is f2. Okay. Derivative with respect to x is just e to the power x plus y. Derivative with respect to y is e to the power x plus y. Right, because the derivative of this is just the, you know, if we had here a 2, then you'd get a 2, but there's no 2 or anything like that. Okay. The third guy is, okay, now some of you are then worried if you did not do math, so all you need to know with derivatives is derivatives of exponents and derivative of products and derivatives of polynomials and maybe the product rule, okay? That's kind of maybe what you need to know. If you're stuck in a quiz on derivatives and you did not do MATH7501 and you've either done derivatives ages ago or maybe never, no, that's not the case. If never, then there's a problem, then tell me ASAP, okay? Let me know. Okay, so you don't need to start making a cheat sheet for all the derivatives. I'll be helpful there where needed. I mean, that's kind of not the key point. It's important, but it's not the key point. Okay, so derivative of f3 with respect to x is e to the power y, and here it's x e to the power y. So there you go, that's the Jacobian matrix. Okay, so that's what we were asked in question C. So I'll just write this. That's df for any xy. Okay. That's a Jacobian matrix. Now, it would have been nice if in the quiz I didn't write that, but it would have been nice and now to have a linear approximation. So let me just add now. Let's now do linear. I didn't ask for this in the quiz, in the fictitious quiz. So let's do a linear approx around x equals 1, y equals -1. What does this mean? What does this linear approximation mean? So I'm going here to the point 1, -1. So I'm going to like this point. And you know, this point with a linear approximation, what I mean is if I now move a bit in some direction, how do I move here in the resulting space? Okay. So for this, what we want to do is we want to do f hat of any point x. I can give you an any point x, but the linear approximation is good locally, okay? The farther I move from z, it's generally going to be bad because the function is typically not affine or linear. We'll do fx at the point 1, -1. Okay, so what was that according to what we saw? Well, it's going to be f at the point 1, -1. Okay, and that's like the exactly at that point 1, -1. It's like we can't do any better. Okay, and f1 -1, I think specifically we computed like here. Well, it's a function of f1 -1. It's this. It's these 3 coordinates. Okay, so I'll just write this. Okay, so I'll actually write it's like 1 times -1, or 1 squared times -1, and then e to the power 0, which is 1. Okay, and then e to the -1. Okay, so that's 1, well, it's -1, 1, and e to the -1. Okay, so that's that. Plus the Jacobian matrix evaluated at the point z. This is our point z. Z, this z. Okay, so plus the Jacobian matrix evaluated that. So I'm actually going to write the matrix now. Okay, and I'm going to write 2 times 1 times -1. Okay, and 1 squared. Of course, these things can be simplified in e to the power 1 plus -1, which is 1. E to the power 0 is 1. And again, e to the power 1 plus -1. Okay, and e to the power -1, and 1 times e to the power -1. Okay, so that's this matrix times x. Let me write it like this. Let me write it. I'll write now x1 minus 1, x2 minus -1. Okay, minus -1. So this here is the z. Oops. This is the z, this guy. Okay, so I just wanted you to see it element-wise. Now keep in mind, these guys they don't vary as x varies. Okay, they were kind of fixed with z. And these guys don't also vary. So that's like our vectors. That's the vector B in the matrix A that we had before. So that tells you, okay, this function f, I mean, it's a complicated mapping, this function. Okay, but locally at the point 1, -1, you kind of know, well, how it's, if you just move a bit, then that's a pretty good approximation. That's your first order Taylor series approximation. All right. Okay. Next question is, can the rank of your answer to C, so now we're in D. Now we're in D. So rank of the Jacobian matrix D, which is the answer to C, be 3. And the answer is no. But maybe I wouldn't ask that. So you can only, the rank of this matrix, if you do here Gaussian elimination of this matrix for any x and y, then you're only going to get at most 2 pivots. So the rank must be less than or equal than 2. Okay. And the last thing, E, is consider now the function g of x is 2 is, okay, so I'll just write it. G of x is 2x squared y plus 3e to the power x plus y minus x e to the y. Can you represent this as u transposed times fxy? And the answer is yes, because you just take u to be 2, 3, and -1. So this is just kind of a linear combination of these guys. Okay. Quizzes aren't beautiful. I mean, they can't be beautiful questions because they have to be quick. It's just kind of to see that we can speak the same language. Are there any questions about this? Can you still hear me? Sorry for asking. I've just been giving you a monologue on the quiz. Was everybody kind of left? Uh-oh, I'm not getting answers. Oh, still here. Thank you. Okay. We've got 9 minutes. We're not going to stop. 9 minutes is 9 minutes. Any questions? Because we have just a bit more to do. Okay. That was this super fast unit on kind of a bit of multivariable calculus. And sorry, let me share the Google Chrome. Oops. And I'll go and we'll actually go to the next file once I can get it in business. Okay. But I see the sharing's not working. Let me stop the share. Start it again. Sorry. Okay. I see. You can see now the desktop. So that's all. That was this quiz. That was this kind of second unit. Let's go to unit 3, and we won't even finish this unit after the quiz next week, because next week after the quiz I want to do some fun stuff with. We'll hopefully speak about the perceptron after the quiz. Okay. Maybe we'll do also a bit of this, but mostly speak about the perceptron. Okay, so we're in unit 3 now, and bright new world. And what we're going to do in this unit is basically speak about slightly more abstract things about vectors and things like that, and vector spaces, and we'll relate that a bit to what we saw with matrices. But at first, we're actually going to speak about something that's very related to what I just showed you. So at least that's kind of related. In this next 7 minutes, we'll speak about a linear transformation. So I just spoke to you about functions that can be kind of arbitrarily general. And, you know, I gave you the exact formulas, but by the way, so you understand, in life, when you do machine learning with such functions, you don't have the exact formulas, but you can compute things numerically. You just kind of have the function. That's roughly, you know, that function could be like a loss function for a neural network. So you don't have an analytic expression for the formula. But now let's speak about specific functions, which we call linear transformations. Okay, so again, a function from Rn to Rn. But let's ask this function to satisfy something. Let's ask it to satisfy that when we take two vectors, x and y need to be vectors in Rn, and we do a linear combination of them with two scalars, alpha1 and alpha2, then we get this property that you get the alpha1 times the function applied to x plus alpha2, the function applied to y. This is called linearity, okay? So when you add two and it's a sum of the additions, it's called linearity, and the other one is homogeneity, but all of this together is called linearity. Okay, so that's what you call a linear transformation. Was this function that we had in the quiz a linear transformation? This function that we just had in the practice quiz, was it a linear transformation? Did it satisfy this property? No, it didn't. Yeah, and alpha1 and alpha2 are both scalars. It's not a linear transformation. Okay. So in general, when you're given most functions, they will not be linear transformations. But the nice thing is that quite a bit are. And what we just did in this approximation thing is we made the function look almost like a linear transformation by multiplying by the Jacobian matrix. But now we're just back to linear transformation. So first of all, let's see that if A is a m by n matrix, and your function just says, take x and apply the matrix A to it, then F is a linear transformation. So let's see this. So prove. So what we're going to do is we're going to do A times alpha 1 of x plus alpha 2 of y. Okay, we need to look at this. And this is A, I should say A times. Okay, this is like times like matrix multiplication. But then from rules of matrix multiplication, that's just alpha 1 A x plus alpha 2 A1. Okay, so you pulled out the scalars, alpha, and you distributed the matrix multiplication to the right. So you just see, and this is exactly this guy. So you've just shown that when you have a multiplication by matrix A, then you have a linear transformation. Okay, that's not so surprising. I mean, you multiply by A, you'd think that's linear. By the way, if you add a matrix B, if you do like plus B, if you add a vector B, this is called an affine function, and in general, it's not a linear transformation. It feels like a linear transformation, but it's not a linear transformation according to this definition. However, in the 3 minutes that we have, and with a bit of percentage that there's left out on the battery of the iPad, I want to show you that the reverse is also true. And that's something that us mathematicians and you as well get excited about. So what do I mean by the reverse? So any linear transformation has a matrix A. Okay, so if f is a function from Rn to Rn, okay, and linear, i.e. f of the scalar alpha 1 times some vector x plus alpha 2 times some vector y equals alpha 1 f of x plus alpha 2 f of y. If this is true, then there exists, that's like nice notation for there exists, a matrix A, okay, such that f of x equals ax. And that A is even unique, okay? Let's not prove the uniqueness, but I want to show you that this exists. Before that, just a few things. What is the dimension of x and y? They're vectors in what space and how many coordinates do they have? X and y, x and y, x and y. N. Okay, so these are n-dimensional. Okay, and these are scalars, just like you guys said before, these alphas. And how about f of x and f of y? What's their dimension? Or how many coordinates do they have? N. Good. Okay. All right, just so we see what we're dealing with. All right. Of course, n can be equal to n, but you know, one of them can be 1 and one can be high dimensional, etc. Okay. All right, so here's a trick. Here's a trick, very simple trick. So what we're going to take is we're going to take the vector x, okay? So x here is in Rn, and we're just going to write it as x1 times 1, 0, 0, 0, like that, plus x2. This is now the scalar. This is the first coordinate of x. x2 times 0, 1, 0, like that, plus up to the last one, xn times 0, 0, 0, 1. Okay, or just using the notation that I already spoke about, we'll write x1 times e1 plus x2 times e2 plus xn times en, where these unit vectors, iPad's just about to die, okay? These unit vectors, because the battery is low, okay? These unit vectors are in n-dimensional space, okay? This is like a dirty trick. I mean, what did we do? All we did is we said, x, it's like taking whoop and expanding it. You know, you kind of have like whoop, all these different coordinates here. Okay. So now let's use the fact that our transformation is linear. So let's do f of x is f of x1 times e1 plus x2 times e2. Now these are the scalars, these x's, yeah? Plus, oops, no, do not die, do not go, do not leave, okay? Plus xn times en. And now let's use our linearity property. And we'll use it n-1 times, because if it happens once, we can do it again and again. So then what we're gonna do is x1 times f of e1 plus x2 times f of e2 plus xn f of en. And this is nothing but a matrix where the first column is E1, is f of E1, and the second column is f of E2, and the nth column is f of En. And we're multiplying it by x1, xn. And there we have it on 1% of the iPad and 0 time left in class. This A is the matrix of this. This M by N matrix A is the matrix of the linear transformation. Okay, we didn't prove it's unique, but it's unique. And we'll speak about that. Maybe after the quiz, we'll speak about this, but slowly, because you'll be tired after the quiz and we'll discuss the quiz. So, but the point is, linear transformations have their matrix A. Okay, and you can actually see what that matrix is by applying F on the unit vectors. So I will actually send you suggestions for 2, 3 blue, 1 brown videos to watch dealing with linear transformations. All right. I kind of rushed through a few things because we took our time with LU. Are there any questions? Oh, okay. Is there anywhere, so Jonathan is asking, is there anywhere that shows the textbook reference chapter pages, etc., for what we've covered in the first 2 modules? Yeah, but the problem is it's quite a lot of chapters, right? So let me actually, first of all, no, there isn't anywhere. And I didn't plan to do this in this edition of the course. But let's open here. So for those of you that have some more time, so I'll speak now about the 3 books, okay? So first of all, the one that you have access to for sure is vectors, matrices, and least squares, okay? And basically, chapters 1 to 10 contain a lot of what we've done, but contain more than what we've done, okay? So that's kind of the problem. So it's not a full thing, but basically, this is an easy read, this vectors, and linear functions we actually just spoke about now, roughly, but this is only like 1-dimensional linear functions. And then norm and distance, we did a whole lot. You even have a homework assignment from 3. And 4, clustering, that was an example we spoke about, right? Now, we did not still speak about sections 5, linear independence, which speaks about Gram-Schmidt and the QR factorization a bit later as well. But we did speak about matrices and matrix examples, but there's too much kind of applications in here for what you need. And we spoke about linear equations. We didn't speak about linear dynamical systems, and we spoke about matrix multiplication, obviously. But again, there's a bit more here, specifically with QR factorization. And matrix inverse is the same, and we even looked at the solving linear equations, but using not the QR factorization. So my point is, you can spend a bit of time on the first 11 chapters here, but just kind of browsing through. I mean, this is a light read, and kind of picking, oh yeah, we spoke about that in the lecture, no, we didn't, etc. Basically, anything that has to do with linear independence, with orthogonality, with QR factorization, we still have not done. Okay, so that's in that book. Hold on, there's something in the chat. Okay, yeah, all right. And then do you need to dive into strength? No, so the point, you do not need to. I think you have enough material from the content that I've provided. But this book, Introduction to Linear Algebra, if you have access to it, then the first 3 chapters are what the first, well, just these. Oh, I see, you don't have access to the full thing, but let me open the table of contents. So first of all, you have access to some things, but basically 1 and 2 is what we've done here, okay? So this is kind of much more close to what we've done, chapters 1 and 2, just 100 pages. Of course, we haven't done everything that's there, but this is also, in a sense, there's a lot of exercises and things like that. If you go to the 3rd book, then linear algebra learning from data, then do we have the table of contents here? Yes, so So basically, the first 4 sections, and this is very dense, but we didn't do section 3. So again, I'm sorry, the order is slightly different. There's not one golden order for teaching linear algebra. So I'm just trying to pick the best that I think is for us. Are there more questions? Okay, so feel free to shoot questions in Piazza. Enjoy studying for the quiz. Don't stress about it. Just make your A4 sheet, double-sided. Also be Friday in the consultation hour. Few people came. Oh, it was ECA here. It was like a public holiday, but that's okay. So Friday, Brisbane time, 11 to 12 consultation. And then I'll correspond with you just preparing for the quiz as well. Okay, bye. See ya. Thanks. Okay, it's nice to see you. Thanks. Bye-bye.